Welcome everyone. It is a very great pleasure to us to introduce our today's speaker, Mr. Sounak Pal, and who is actually a PhD student at IIT Gandhinagar in India. And his today's lecture is based on low-dimensional quantum gravity using Virasoro thermo-quantum field theory. I hope this will be a very interesting lecture, and I think you can start talking, Sounak.
Okay, so I am audible, right? Properly?
Yes, you can. You are audible.
Okay. So to start today's talk, let me. This work has been done with collaboration with my guide, Professor Arpan Bhattacharyya, my collaborator Saptasha Ghosh, and Paulami Nandi, who is a postdoc at University of Pennsylvania. This is based on a. This talk is based on the current recent work we have done. So I will, without wasting more time, I will just start. So what this presentation is all about is basically we. So if I annotate something on the screen, you can see, right? Hello.
Can you hear me?
Yeah. So if I annotate something on the screen, you can see, right?
Yes. No. It is okay.
Okay. So the regime of 2D gravity with the disks, trumpets, and wormholes. This will become clear in the due course of time what these things are. Then I will talk about the modifications and problems what we face when we start doing one-dimensional higher gravity. So it's 3D gravity. Then I'll talk a little bit about what is chaos in 3D gravity with wormholes. And then I will conclude with some future directions, and I'll talk a little bit about the Higgs splitting if time permits. Okay. So the brief outline of the talk is basically I will briefly motivate why we are interested in the 2D gravity regime instead of the 4D. Hyperbolic, then I will talk about what is the hyperbolic modular space for our calculations. Then I'll talk about some models of three-dimensional quantum gravity. Then I will talk about the chaos and motivation. So why 2D gravity? So instead of 4D gravity, the first and foremost reason is to study the aspects of quantum gravity in the lower dimension is its richness. So you can almost study all the properties of 4D gravity. So it may be it's more tough in 4D to think about the path integrals over G mu nu and all things like that. So let's start from some lower dimensional case that is 2D. Now the point is the Einstein gravity is has no propagating degrees of freedom in 3D. So now the question is, can we proceed with the agenda to get some result in ADS4? Okay. So ADS stands for anti-de Sitter space. So what we are actually aiming for is to calculate what happens in anti-de Sitter space in 4 dimensions. So we can proceed only if we understand the basics of JT gravity model very clearly. So it comes from a 4-dimensional model when you dimensionally reduce it to 2 dimensions. And then the next question appears. There are several, developments in now recent times that we need to do a path integral over G mu nu, and that is called the gravitational path integral. So why we do need this sum over all sorts of topologies? So is there any other way that we accept the sum to get the modular invariant gravity partition function? Let's say in ADS. So if we have to sum over all sorts of topologies, that is the usual way to get the modular invariant partition function. But is there any other way to do the bypass the process of doing the sum over all possible topologies? So the answer to this question is yes. You can. There is something called gauging the symmetries. So in gauging global one-form symmetries in the bulk, you can get different. I mean, the connected components will disappear, and you get a factorized answer. So this will become clear when I will proceed. And why also 3D gravity is special? Firstly, in 3D gravity only, you can write down a gauge invariant action in terms of the SO 2,1 omega is a spin connection. So omega is a SO 2,1 gauge field. If it's Euclidean, then it's SO 3. Otherwise, it's in Lorentzian, it's SO 2,1. So which can be combined with the Werbine E. Now, infinitesimal coordinate transformations and while rescaling. So you start with your 3D Einstein gravity action, and you want to see what is the, can we write it down in terms of some gauge field. So the point is, if you write your gauge field A in combination such that omega plus E and omega minus E, you define A plus and A minus in such setup, then you can write down the Chern-Simons action, which comes from the Chern-Simons functional as trace over A minus GA minus and 2 by 3 A minus cube, and another copy is from A plus. So you can already see that there are two copies. One is forming from omega plus E, the other one is forming from omega minus E. And these are called left moving and right moving. And these K labels the whatever. When we'll go to the universal covering of this SO 2,1, we will get SL2R. So this SL2R gets, this SL2R symmetry has a label K. So this K comes from that level. Now, you can have different coverings of this SO21 cross SO21. Why it's 2 SO21? Because you have a left moving mode and right moving mode. Now, the point is, you start writing your gauge field as some omega 0 E like this, where omega is a 3 cross 3 block and this E over L, sorry, and these are just columns and last column and last row. So the point is, if you write it down in that sense, that you define your A mu A as omega A mu plus some L inverse, where L is the ADS length scale, and omega A mu minus L inverse E mu, you can define A mu A plus and A mu A minus similarly. Now the point is, here omega A mu is a SO 2,1 gauge field, and it's called the spin connection, and EMU is the variable. Now, from the gauge field side, if you see only from the perspectives of the gauge fields, then this A mu A, nothing stops it from being 0. But the point is, from the right-hand side, you can write whole Einstein action in terms of these omegas and E's, where you want the metric to be non-degenerate because of the positive distance. You need to define a notion of distance. So for good metrics, these omega and E, this combination has to be non-zero if you demand that the metric is non-degenerate. Then there is an invertibility problem, right? So if EMU is becoming somewhere at 0, then one hand side of the, you want to write the Einstein 3D gravity in terms of the gauge theory, where you get 0 in one side, or the other hand side is not. So so this is a problem of invertibility. So that's why we cannot exactly say that pure 3D gravity can be reformulated as a gauge invariant action. Now, as said by Wheaton, that there is a gauge invariant action only in 3D. So the point is, you can write your gravity action in terms of these gauge fields, but this is possible only in 3 dimension to write it in a gauge invariant way. Now the point is, if you start considering the topology change from the gravity side,
Can you ask something? What is L inverse?
L is the ADS length scale. So
Okay.
L inverse. So I should have defined K equal to this Carly L by 4G, which is related to the central charge of the boundary.
Okay, I got it. But I had other concern is that I understand the omega is the algebra element of SO21, but A mu plus A mu minus A, which involve the VL bind, it is a algebra element of inhomogeneous 2 plus 1 Lorentz group.
Can you repeat what is the?
Whether this A mu plus minus A is the algebra element corresponding to the algebra element for inhomogeneous.
No. So the point is, this A mu A. So you need to define JA with this. So this A mu A JA is so JA comes from the SL2R. So these are the components, but you need to multiply with some j.
I understand, but what is the corresponding generator for omega A and E mu A? Omega mu A associated with the generator for the Lorentz group with 2 plus 1. And I think E mu A, which is called Vierlein, associated with the gauge field, associated with the algebra generator with the translation, right? So you need the translation. Otherwise, how can you define this Vierlein from SO21?
Yeah, that is fine. I mean, from SL2R side, these GAs are the generators.
No, I understand the SL2R is okay to define the spin connection part, but how to define the Vierlein associated with this SO21 group? Do you need the inhomogeneous Lorentz group, which is the Poincare group?
Yeah, the whole Poincare. I mean, SO21 is this omega 1 mu. So two copies of SO21 is coming
SO21
from.
only offered the omega part.
Yes.
And E mu cannot come from the inhomogeneous SO21. You need inhomogeneous one. I mean, ISO21.
Yes, this is the this is the whole Poincare. Yeah.
So A mu plus minus A is the corresponding the gauge field associated with the one from which is nothing but the algebra element with the inhomogeneous Lorentz group. Am I right?
Yes.
So, okay. So why then you are
you mean inhomogeneous Lorentz group is Poincare, right?
Okay. Okay, I understand. So therefore, you are now considering the connection one from as a algebra element of ISO21 to write down this chance
Euclidean. Yeah, I mean, yeah, yes. So the point is this A mu A, this has to be contracted with JA. The JAs are the SL2R algebra elements. So
yes. But J only contracted with this omega A part, spin connection part, and E mu A contracted with the P mu, I mean, or PA, which is translational generator.
Yes.
So therefore, this you are now particularly gauging the inhomogeneous Lorentz group.
Yes.
2 plus 1.
Yes.
Okay, I got it. Okay.
Only the inhomogeneous part of the.
Yes, I understand.
So this is one there is a problem with the invertibility. Now the problem with other thing is, so if you consider that you have all sorts of, so if you do a gravitational path integral over all possible metrics, G mu nu, then you can say,
sorry,
yeah.
Can I ask a question regarding? Yeah. So you have omega here, a mu, like a is running from, like, is it running? Is it the same a that you have on the a mu? Because
so this A mu A is going to be contracted with JA, right? So these SL2R generators has all the A will satisfy. I mean, A will all be the element of SL2R generators. So how many number of generators that comes from SL2R? Let's say they have for let's say 3 generators, then A will run from 1 to 3. So that depends on the universal covering of SL2R.
All right. Oh, okay.
Okay. Thank you. So thanks for the question. So yeah. So now the point is, so this is the first problem with that, and the next problem is the topology change from gravity side. When you do a gravitational path integral, usually we can have G mu nu, which is varying in quantum gravity. So you can set your G mu nu on a fixed topology in many ways. Out of them, when you are doing path integral, the Saddle solution, one of them will be a solution of the Einstein gravity, but it is not fixed. I mean, G mu nu can vary over all possible sorts of things. So that's why we'll see in the next slide why these sorts of different topologies come in. So we'll start with the 2D gravity with disks, trumpets, and wormholes. Why these sorts of geometries come in, we'll talk about that. So, so there is a fairly general class of 2D dilatant gravity action where you write your action as minus S naught times chi, where chi is the Euler characteristic of the manifold you are defining. And then you have minus 1 over 8 pi gn times this whole phi here. Phi is the dilaton field with R is the Ricci scalar. And then you can have a general dilaton potential, which if you couple your 4D theory with some non-minimal coupling, non-minimally coupled gauge field or non-minimally coupled any field, scalar field or whatever, then you will get a non-trivial U phi that may not be linear in phi. But in general, when U phi is some function of phi, let's say phi to the power 3 by 2, phi to the power 5 by 2. So whenever we have done the non-minimal coupling, there are many possible powers of phi that starts appearing. So you cannot generally do the path integral. So when you are trying to find out the partition function, you need to path integrate over all such phi and all such G mu. But usually it is not possible to do the path integral with arbitrary powers of phi. So what you need to do is to expand this U phi around the saddle and take the contribution, linear contribution. If you turn on the higher order phi square or something terms like that, then there is a non-trivial back reaction from the boundary. And if you couple, let's say, a gauge field in 4D, then if you dimensionally reduce to 2D, your space-time, which was previously ADS, because if you write down this phi r minus 2 phi, then if you path integrate over phi, you will get r minus 2 becoming, so it should be r plus 2 becoming 0, which sets r equal to minus 2. So negative Ricci scalar constant, which is ADS. But the point is, when you have a trivial, non-trivial back reaction, then your r, Ricci scalar, can be changed. I mean, it's not fixed. It may be a function of charge. But we can see that if you have 1 over q squared, we'll have, if we consider the global one form charge to be very large of this gauge field, then you can write down it to be, take it to be ADS in 1 over q square perturbation. Okay, so let's start with the basic setup with TD gravity, which is the JT action, where you start, you have phi r minus lambda. Lambda is the cosmological constant, and we have taken the dilaton potential to be a linear potential in phi. And the other copy is basically the boundary term, which is root gamma u, phi times this k is the extrinsic curvature, which happens to be a Schwarzian term if you consider disks. So whatever, so in 2D gravity, what possible topologies can we have? So the possible topologies we can have is firstly a disk. It has, so in gravitational path integral, if I try to write it down, it is possibly an integral over dg mu nu, then your e to the power minus s, which is some function of g and phi, you need to sum over all possible topologies also. Now, when you sum over all possible topologies, you have the genus zero contribution. You may have, so this is basically defined by the Euler characteristics. So you can have different class of geometries where.
I had another comment. What do you mean
Yes.
by sum over topologies?
So here I mean sum over topologies means different topological manifolds.
Okay, so it is not necessarily the Riemannian manifold.
Yeah, that will come as a second restriction, that your manifolds need to be hyperbolic and Riemannian. So your G mu nu has to be, has to be smooth.
I want to understand actually.
Yes.
Your path integral measure clearly indicate you are summing over all possible geometries.
Exactly. Yeah.
But why? Does it not indicating that when you summing over all possible geometries, topology is already incorporating this in terms of this sum?
No. So this G mu nu is not the fundamental one. If you define a manifold with a specific, let's say, a topology, let's say you define, start with a space M, which is a set. Now you define some theta on it, which is a topology, standard topology. Then this M comma theta is a topological space, but it is not a differentiable topological manifold. That would be only a.
Sorry, could you clarify, please? What is theta?
So theta is a standard topology.
Topological index, right?
What do you mean by topological index?
I mean, what is the characteristic character defined by this
Okay,
topology.
so if you have a set M, then you can define row of M, which is the subset, all possible subsets of M.
Okay.
Now you define theta, which is the topology
I got
defined.
it. I got it. You're considering some manifold endowed with some metric and incorporating with some particular topology defined in terms of theta. Okay.
Exactly. Yeah.
Then you are summing over this manifold in terms of G mu nu.
Yeah, better I can say, I mean, to remove the confusion, I can write topological manifolds.
Okay.
So is your confusion clear, or I should explain more?
Okay, you can go ahead. If I had other question,
Yeah, we can discuss it at the end. Let's see. Okay, yeah. So the first thing we face is that now the point is, why should we sum over all sorts of topological manifolds? The answer to this question is basically twofold. So firstly, we need a modular invariant gravity partition function. Now this modular invariance will not be very clear in 2D, but when we'll proceed to 3D, it will be more and more clear. Okay, so the point is the boundary theory of enough to understand? If yes, then what is the breakdown criteria in higher dimensions? So the question I'm asking is, if you have, let's say, a 2D such sort of topological gravity, then is it enough to define a single boundary theory at the boundary, or you have to define an ensemble of theories? What they mean, the ensemble of theories, is that when you have this path integral over all possible G mu nu's, these you can term in terms of, so if I can erase this portion, then I can, let's say, write this dg mu nu as an integral over df and integral over the bulk moduli. So you can, if you don't know about this, then just take it as note that if you have this contribution fully comes from the boundary, and this contribution fully comes from the bulk. Okay. Now this f, which is the parameter of the boundary wiggles. So let's say if you have a disk, then you can define a weakly boundary in the case. So here he says, so as ADS CFT suggests, that there should be a CFT1 at the boundary. But the point is, as I was saying, that for the CFT1, the trace tensor has to be traceless. But the point is that means TZ bar plus TZ bar set has to be 0 in 2 dimensions if we have a CFT2. But the point is, here we don't have ZZ bar coordinates. We have only one. So that means you have to have your TZ equal to 0, which is not the case if you couple, if you have a pure gravity theory. So now from the boundary dual, you have boundary edge modes and your TZ is not 0. So the point is, what is the resolution to this? So the resolution is, you integrate. So instead of dividing by all possible this, so why we are dividing? So when we perform the integral over dg mu nu, we do the following. So it divide by the volume of the gauge group, right? So let's say for disk it's SL2. So SL2C. So the point is, why we divide by this volume is this is coming from the disk isometries, the diffeomorphism symmetry at the boundary. So now the point is, if you change this wiggly boundary to some different wiggly boundary, that is some different f, right? So you need to, so f is defining whatever choice you have in the boundary. Now you are integrating over all possible f's. The reason is, you cannot map, because the conformal symmetry is spontaneously broken in a JT gravity, because there is a CFT1 and this is not holding. But in ADS3 CFT2, it may hold that this you can. That's why we have a different sort of path integral in ADS3 CFT2, because there is the spontaneous symmetry breaking is not happening at the boundary, and your symmetry is restored. The conformal symmetry is restored. Okay, fine. So now the point is, how would I perform these all sorts of complicated path integrals over these DG mu nu's, things like that. Okay, so you can have so as I said that you can have different topologies. So the first topology comes with the, so this is only one boundary. So you can have G comma N, because the Euler characteristic goes with the manifolds G and N. And then you have a genus and the number of boundaries. So the basic case is you start with single boundary without any genus. Then you go forward, you define some one boundary, but you can have some genus in the bulk. Then you define a single boundary. Then you can have two genus in the bulk, and so on. So this is you are fixing N and you are summing over all possible G's. Then you can have a possible choice of two boundary case where you have a wormhole, because this is two boundaries, two ADS boundaries asymptotically, and you don't have genus in the bulk. Then you can have these sorts of geometries, and so on. So when you are doing the path integral, you need to calculate all possible sum over all possible topologies. But it is, I mean, it is very tough to consider all possible topologies. There should be some perturbative parameter that will suppress the higher genus topologies, and that is there in 2D. So the disk come with exponential of S naught, and the other factors come with exponential of minus S naught and exponential of minus 2 S naught, or so on. So for large entropies, you can say that this disk contribution will be exponentially, will give an exponential contribution, and the other contributions are exponentially suppressed. So basically, genus zero contributions in more boundary cases will be more and more prominent and important. Okay. So far, so good. So we start with the ZGN and we define a path integral of all possible fields as we calculate the path integral over G mu nu and phi, and we divide by the volume of the diffeomorphism. So this diffeomorphism redundancy is taken care by the volume of this diffeomorphism. Now, in this part of the talk, we'll need to give most care of 1 and 2 point functions. We'll not go to the, you can calculate 3 point and 4 point functions, but let's see how to calculate 1 and 2 point functions. So if you try to calculate the 1 point function, you will get this contribution with, so their contributions are basically these type of contributions. You have a bulk moduli which takes care of this bulk piece here. I mean, it gives the contribution of, so there is a moduli space. So this BG1 is basically this moduli space volume. When you are doing the path integral over G mu nu, you have the integral over all possible bulk moduli and boundary wiggles. So these boundary wiggles are coming from here, and then the bulk information is coming from here. So as defined by Mizakami, there is a relation between these hyperbolic. So these are hyperbolic volume, moduli space hyperbolic volume, and these are dependent on these. So how these are connected is basically these are called geodesic boundaries. So if you glue two trumpets, let's say, or if you have, let's say, manifold in which you have a single genus in the bulk, so you define your moduli space with like this. So you cut yours. So I can do the surgery here. So if you have a space like this, then you can cut something like this here, and you'll get something like this. But here, this is not a asymptotically ADS boundary. This boundary is a geodesic boundary of circumference B. And then you have another B, and you have this genus in the bulk. So you glue these two things together, and you have an integral over dB and times B. So this is the measure for gluing these two surfaces. So when you calculate this 1 point function, you will have only one asymptotic boundary. When you calculate 2 point functions, you can similarly proceed and calculate these Z beta 1, Z beta 2 2-point functions. Now the point is, when you calculate the wormhole, how do you calculate it? It is basically, you can break this wormhole into two pieces. So this is basically this, where you have these two boundaries are geodesic boundaries. So you have integral over B, and then you glue these two trumpets. So these basic blocks are called trumpets. So you glue the two trumpets with specific boundary length beta 1 and beta 2, and you do the path integral, and you get the Z02, I mean the wormhole partition function. So the Schwarzian disk partition function and the trumpet partition function can be calculated by evaluating this path integral, and you get these expressions where you have beta as the boundary, asymptotic radius boundary. Okay. So I will now talk a little about this spectral form factor, which is a probe of chaos, but it's a late time chaos. So you insert two operators in the boundary of, let's say, a disk, and you calculate what is the correlator of this OT and OO. Let's say we calculate the matrix elements inside the complete set of states and calculate what is the OT and OO. Now, if it is true for general conformal dimensions, delta, it will also be true for delta equal to 0. So you can set the conformal dimension of these operators to be 0, and what you get is the partition function, but that is analytically continued. So you have Z beta plus IT and Z beta minus IT. So what do you mean by Z beta plus IT? Is you have, so this Euclidean, so beta is the Euclidean portion. So you do a half disk path integral. Okay, so this is beta by 2. Then you evolve it for a Lorentzian time t by 2 on both sides. Then you glue it back with again a length of beta by 2. And what you get is beta plus IT. Right? So you take the product of beta, so this is evolving in this direction. Now beta minus IT evolves in the opposite direction. So this direction will be opposite. And you have different sorts of, so if you take the Z beta plus IT, Z beta minus IT, this is the disconnected SFF. You can also calculate these type of things, which is Z beta plus IT, Z beta minus IT, which is a 2-point function, but this is beta 1 and beta 2 can have general. So these 2-point functions are not factorized to Z1 beta 1 plus IT and Z2 beta 2 minus IT. This is not this. The reason is you have a wormhole connecting the two boundaries. So this is not actually a factorized answer. As you have wormholes in the boundary, then this answer is not like just like this. Okay. So that's why this connected spectral form factor behaves differently than the disconnected spectral form factor. And this, what is the description of this connecting wormhole? Is that you have an ensemble of theories in the boundary, not a single theory. And what do you mean by ensemble of theories? You have a boundary mode which is propagating through the circle, diffeomorphism 1 is 1. And these boundary modes are parameterized by f, and you do a path integral over all possible f. So that's why I am saying that there is a all possible theories, ensemble of theories in the boundary. There is other way to gauge the bulk quantum symmetry and get a single quantum system in the boundary, but we'll not discuss this thing here. We'll talk about only ensemble. Okay. Now, what are the modifications and problems we get in 3D gravity? So the point is, we start with the super level theory, as our work is based on super level. So why this theory comes? So let me first talk about a bit why this thing comes and so on, things like that. So the point is, when you try to write down path integral formation of the 3D gravity, it is quite tough because the surgery techniques are more involved. When you cut to the wormhole, you get some sort of things like a geodesic boundary here, a geodesic boundary here, and so on. But in 3D, your bulk manifold is 3-dimensional, right? And you can have 2D manifolds, so you can have a torus on the boundary. So when you're cutting the bulk, you can have torus. So the gluing procedure is not integral BdB, right? And the second problem is if you have a torus, it starts with the most thermal ADS3, which is basically a torus, which I have already drawn here. So this diagram is basically we can have non-trivial gluing performation for these sorts of ADS3 manifolds. So how do you do the gluing techniques? We'll study for TQFT. So I'll get back to the slide a bit later. So firstly, I will motivate how I to study the 3D gravity. So in 2D gravity, we had a perturbative parameter, which was e to the power minus s naught. But in 3D gravity, there is no specific theory parameter, which is like e to the power minus s naught. Now, topological surgery techniques are more challenging. So performing the path integral for higher general surfaces becomes more and more tough. Now, ensemble average, doing the ensemble average of the boundary theories, it has been shown in recent papers that if you don't consider non-Gaussian contractions, then these type of things will not give you back the modular invariant partition function of the 3D gravity. And the higher genus partition function calculations needs more and more involved topological surgery. The optional partition functions that I will not discuss is needs is Charn and Knot classes, and the another interesting extension to gauge supergravity to show. So these things are basically what I was talking about is that you can have a modular invariant partition function in the bulk if you gauge the one form symmetry in the bulk or p form symmetry in the bulk, or you can have a ensemble average. So this when you gauge the one form symmetry in the bulk, you will get a closed manifold partition function equal to 1. That is trivial. But that is also a way to get the modular invariant partition function of 3D gravity. But we can get rid of, we can discuss it later. Okay. So instead of doing gravity, as I said initially, that we had a problem with doing the path integral, you cannot do a Chern-Simons theory, proceed with the Chern-Simons theory of 3D gravity. What we'll do is we'll start with the topological quantum field theory, TQFT versus gravity. So what we'll do is basically, so the point is there is a phase space related with this TQFT, topological quantum field theory. There is a phase space related with the gravity. But these large gauge transformations of the gravity side. So these large gauge transformations means these gauge transformations which are not continuously connected to the identity. It may satisfy the boundary conditions of the gauge field, but it may not follow up that faster. So the large gauge transformations of the gravity side is not included in the topological quantum field theory, because you can see from here that this Teichmuller, which is a TQFT, this contains all the matrix sigma, and it is divided by Weil cross diffeomorphism, where diffeomorphism is diffeomorphism 0. So these are all small diffeomorphisms which are continuously connected to the identity. Okay, but when you gauge gravity, you have to divide by all sorts of diffeomorphisms. That's why I have written the gravity path integral have all sorts of diffeomorphisms, all diffeomorphisms. So what is the process way to define, what is the way to match these two phase spaces? So what you do is basically you divide this, you replace diffeomorphism 0 by diffeomorphism, and you multiply diffeomorphism divided by diffeomorphism 0. So then you will get a relative mapping plus group, which is the mismatch of gravity versus TQFT. So when you calculate the gravity partition function, you need to insert this. So by using TQFT, you need to insert this mapping plus group. So this is called mapping plus group, and which is basically the large diffeomorphisms, because you are seeing here that all sorts of diffeomorphisms are modded out by all sorts of small diffeomorphisms. So the point is, when you consider, let's say, a disk, which is a 2D asymptotic boundary, these large diffeomorphisms act trivially on the boundary. But the point is, when you have 3D in bulk, then your boundary is a torus. And large diffeomorphisms act as modular transformations of this torus, on the torus, SL2Z modular transformations. So you need to take care of that, and you need to sum over all possible modular transformations that are on the bulk, that are on the boundary. So there is a apparent mismatch between these two gauge groups, And what we'll do is we will try to recover this by using this. So this was first, proposed by Everard et al., which said that if you start with Virasoro, Z Virasoro partition function, and you do the mod square of that partition function, and then you sum over all possible boundary modular transformations, then you get what you get is the gravity partition function if you divide it by mod map of m del n. Right? Now the point is, can we extend it for the super Virasoro case? And then we can we get what is so if we include fermions, can we get this super gravity partition function? So in our paper, we have shown that yes, it is possible that if you start with a super Virasoro instead of Virasoro, you will get a supergravity partition function. But that needs certain technologies, because previously you don't have a spin half particle because the Liouville field was a scalar. Now these Liouville conformal blocks that we will get now will be super Virasoro conformal blocks, and that have a spin because these fermions have a spin half particles. So the spin structures can be different. This can be this when you are having a scalar field phi, that is basically having so it can join with e to the power 2 pi I phase, and these spin half particles, these fermions, can join with different spins. It could be odd or even. So there are two different spin structures. It could be odd spin structure or even spin structure. So we'll talk about that. Okay. So now, what this recent paper of Eberhard, Collier, Berlin they proposed was that if you take the so the first point is, how do you calculate these Virasoro partition functions, which is the building block for calculating the gravity partition function. So the point is, you define the inner product of two conformal blocks, which is basically CFT conformal blocks on the boundary. Then you define the inner product this in this way, which comes from, if you start from this diffeomorphism invariant theory, you can define the inner product of these conformal blocks, which we have derived in our paper also, that how to get this time-like. So this gives the time-like super Liouville part, which was basically time-like Liouville for their case, because they were working with normal gravity, non-super gravity. So time-like Liouville. So I am saying what I am saying is basically 3D gravity has a correspondence with 2D Liouville theory, but it's not a boundary to bulk correspondence. It is basically a correspondence which comes out. It is emergent. So it's not a boundary bulk correspondence. If you have a bulk boundary correspondence, then if you have, let's say, so that you can understand from the previous slide, because if you have two, so this is square, right? This is general. You have to mod square and then all sorts of take the sum over all possible modular transformations. Then if you have three boundaries, you should cube if you consider the Liouville theory in the boundary. I mean, it's a boundary dual, but you are not doing that. So so what happens is basically the Teichmuller phase space becomes a product of two. So basically the gravity phase space. So the gravity phase space becomes one copy of Teichmuller becomes another copy of Teichmuller. So these two Teichmuller TQFTs, one is called the, so if I use some terminology, these are the holomorphic sections of the flat SL2R bundles. What do I mean by flat is integrable. So that means you can start with a manifold, you define a connection, and that grad square of that connection is 0. Now, the other one is the non-holomorphic, I mean the anti-holomorphic sections of the flat PSL2R bundles. So these are these tau and tau bar. And the gravity phase space is basically becomes equal to that. So that's why we have two copies.
I had a concern. What do you mean by gravity phase space? Okay, could you clarify again?
So what we are trying to do is basically here this. What do you mean by gravity phase space is we have a left moving part and the right moving part. Right. So this is not a basically, so this phase space is in the concern of geometric quantization, not in.
Do you believe that this is a cotangent? This is a cotangent bundle?
Which one?
this gravity phase space is one of the cotangent bundle, as is just we did in a classical mechanics case.
So the cotangent bundle of what?
I mean, gravity phase space, can you visualize? It is a cotangent bundle. I mean, instead of, phase space
So the
has some
cotangent
specific
bundle is
structure.
basically if you
I mean,
start with
when you
the
talk about phase
cotangent
space,
bundle is basically if you start with the let's say T, which is the tangent bundle, you take a T star of M, right? And if the M is basically containing the all sorts of points X, then you
yes, phase
define
space
all
is
sorts
one
of
of the
points
example of
Y.
cotangent bundle.
Yes, it can be, yes.
So therefore, what does it mean by phase space? I mean, in the context of gravity.
So this phase space basically means what is the gravity Hilbert space? I mean, this phase space is so what? How can I explain? So the point is you have holomorphic sections of this line bundle of the PSL2R. So that those are basically this Teichmuller phase space, which is tau and tau r. So you have holomorphic and anti-holomorphic, which matches with the gravity phase space. In the gravity phase space, I am becoming. So what I am saying is basically these diffeomorphisms, which are on the which are the small diffeomorphisms in the Teichmuller side. This becomes we have to gauge by all diffeomorphisms in the gravity phase space. So the gravity phase by gravity phase space, I mean that you have to take into consideration of large diffeomorphisms.
Does it encode any symplectic structure?
Yes, it encodes. So whenever you have this, so that's what I'm saying. If there is a y and there is a x, half of them will be these position basis and half of them will be
Is
momentum.
a momentum like.
So now what you can define is basically, and whenever you have this cotangent bundle of structure, this omega that you define is basically dx wedge dy. That is the more fundamental one.
Is a two form.
Yeah.
Corresponding which encode the information of symplectic info structure.
Exactly. It is a two form. So that's why these tau, these are z, dz type of thing, and this thing is the dz bar type of thing.
Okay, fine.
Yeah, but yes, you can see this as a cotangent bundle. But yeah, I mean, yeah, from the gravity phase space, you can define a manifold and then. So what I think is basically if you define a manifold, then you first define the connection, which is more fundamental. You demand this connection to be integrable, which means grad square equal to 0. Now you define a pre-quantum line bundle, which is capital L, and on that line bundle, you can define this. From that line bundle, you can do all sorts of things like define a one form, which connection one form which satisfies this grad square condition equal to 0. Something like that.
So your quantum theory now based on this gravity phase space, right? Just
yes.
like a phase space path integral in quantum mechanics.
Exactly. Yeah.
Okay.
But that has a mismatch with the TQFT phase space, but that will match if we divide by this mapping plus.
Okay. Okay.
I mean, not mapping plus group, this map type of things. But this a sort of mapping plus group because large diffeomorphisms are acts on the boundary as modular transformation. So you have seen, I guess, this. So the modular parameter tau of a torus, which if you see, this is basically tau. So what is torus? Torus is basically a rectangle where you identify these two sides, right? And you have a lattice where it is tau. This is 1. Right? So basically, the q is basically exponential 2 pi I tau, and we write the partition functions every time inserting q. So the modular parameter tau goes to just SL2Z transformation, tau plus t over theta plus t, and so on.
Okay.
So that's what we are doing. So we have a transformation of the modular parameter going to eta plus b by theta plus t. And then if we define this as a gamma acting on tau, which is equal to eta plus b by theta plus t.
By the way, Shonak, I just want to mention you have only 10 minutes.
Yeah, I guess these are more important parts. Other parts I can go faster. Okay, great. So far so good. So we'll define this inner product of conformal blocks as the integration over the Weil-Petersen volume, but it's for Liouville, it's the super Weil-Petersen volume. And you define just the ghost partition function. So you define your theory in such a way that your central charge becomes at least, I mean, your central charge should. So if you define from the string theory side, your central charge should be head up to 0. It should be cancelled. But if you, in this theory also, this ghost but thing has a central charge of -26, and this time like super Liouville has a central charge of 26 minus c. So it turns also central charge of c. Okay, if you adding things, c minus 26. So, yeah. Okay. So the point is, whenever you have these sorts of, now what you can see is basically, if you want to, how do you calculate the gravity partition functions is that. So let's start. So we are trying to calculate the super torus partition function, okay, and using the conformal blocks. So what we will do is basically, if you do from the path integral side, you need to calculate what is the conformal block on the torus, because what is the conformal block on the torus, and that is basically, if you define the partition function, that is a 0-point conformal block, because I mean, if you have insertions, that is that may be 1 point, 2 point, 3 point, or whatever, but if it's a 0 point, it's basically the character of the group. So the point is, we define your Liouville field phi a as exponential of a phi sl. This is the Liouville thing, and these are all these coming from fermionic contributions. So if you keep it aside, you can calculate the super torus partition function. So let's say we have a boson on the torus, and if you have a boson on the torus, which is a free scalar, then you have this d phi d psi d psi bar integral, and basically given by this determinant of grad square to the minus half times half times, and you calculate it to this thing. So how to calculate the partition function of let's say more involved topological surfaces is basically, you start with some, let's say you start with some this type of sphere topology in the boundary. Okay, so this is basically S2. Now the point is, this chi has to be negative because we need hyperbolic manifolds. So this chi is basically, you can write as 2 minus 2g minus n, or you can write it as, I mean, it's a more general formula, but you can write it as -1 to the power n times h1 of this manifold m you are considering. So this is an alternative sum, and this h1 denotes the homology of this manifold you are considering. But you can take it as a general formula that so you have 2 minus 2g minus n. Now in a sphere, if you don't consider any insertion, then it is not a hyperbolic manifold, because your genus is 0. So you get 2 minus 0 minus, whenever you have 3 insertions, you can think it as 3 punctures, so 3 boundaries. So this is -1. So your chi becomes negative. Whenever you have the number of insertions less than 3, you will get chi to be positive or degenerate. So that doesn't contribute. So we cannot calculate those partition functions via this technique, because this is only valid for hyperbolic manifolds. Okay. So the point is, what is the conformal block on the boundary for this type of 3 insertions? That is the 3-point function, which is Cijk. Okay. And here, these are the structure constants. Okay. And here also we have Cij. Right? But when you define the inner product of these 2 conformal blocks, you follow a prescription that this P1 and P2 has to be orthogonal to each other. I mean, this I have shown here, that this satisfies, if you take the inner product, it has to satisfy this delta P1 minus P2 condition. On top of that, you can have certain contributions, which is basically, you will have rho SCGN, which is given by omega 0s times CNS. So these are the structure constants, CNS times omega 0s. So if you have cups in the theory, in the manifold, then you have to introduce these factors. Otherwise, you don't need. If you have, let's say, so what do you mean by cups? Is that you have a complicated genus topology. So let's say a structure like this. Then, so if you have to cut it here, you have to cut it here, then you have to cut it here. Then you can see that if you cut it like this, you'll have a pant, which is the more fundamental thing for us. So the pant is basically a 3-sphere, which looks like this. Okay, so this is a pant. Now, if you cut it here, you can imagine that this will open up these two things, and the another thing is basically this boundary. So this boundary corresponds to this, and if you cut it along this thing, you'll get two things. So what you need to do is to, for doing the surgery, you need uh, cups. Why not less than two bounded? Why not less than three boundaries? Because you need to divide the whole manifold into three boundary pairs. Otherwise, you will get not a hyperbolic manifold, because the fundamental things will not be hyperbolic, because we need three insertions. Only then they will be hyperbolic. Okay. So the point is, now what you are considering is basically you calculate this rho SCGN, which is the product of these cups and pair of ends. Then you can define what is the inner product and calculate what is the partition function, because this will be basically become equal to Z Virasoro. And what you need to do is to follow this prescription. But this may be for super Virasoro, it will be super Virasoro. And you calculate what is the modular transformation, and then sum over all sorts of modular transformations. But there is a certain point. There may be cases where the boundaries, these modular transformations, may not act non-trivially on the boundary. So this, so for torus, the group is SL2Z, but for sphere, it is trivial. So the point is, there is no non-trivial modular transformation that you need to sum over. So the sum is gone. So that's why this partition function is basically this. But if you have a torus, then things become more subtle, and you have to sum over. Also, you start with this type of thing. So this is the partition function of the torus, which is basically, you can write as Z super Virasoro, and you have to mod square this thing by applying this transformation, which is this. That's where I have written this super Virasoro partition function is just the product times the sum, where you have gamma tau 2 and gamma tau 2. Okay. Now, depending, as I said, that depending on the spin structure, these type of things can be different. That this gamma acting on tau 2 would be this, depending on the spin structure, you can have, for odd supergravity, you can have a different modulus sum, whereas for even supergravity, you can have a different modulus sum. Okay, that depends on the spin structure. So what I mean by odd and even is basically the boundary conditions. So when psi is basically, let's say you start with tau plus going to tau plus some values, tau plus a, it's replaced by e to the power 2 pi I a times psi of tau. Okay, so this whatever this value is changing. So if the fermion is like, it's starting with psi, and when it goes to the other boundary, it becomes minus psi. That means there is a twist in between. It has a twist. Whenever it has a twist, we say that is an odd boundary condition. Whenever there is no twist, it is called the even cases. So there are different boundary conditions where we can we'll change the partition function. Okay, because this is also expected from the path integral. Now I'll not go into this compression body things. This is more involved calculation. So now the point is, if you want to calculate the torus 2-point function, let's say we have to include, so inside the torus you have two insertions here and here, which you can see as a boundary. Okay, and you can calculate these conformal blocks in these torus by doing different surgery techniques. And this was first done by this Jan and Hartmann, who said that you can calculate the 2-point functions and take the ensemble average to reproduce what is the partition function, but there is a certain mismatch. So exactly the 3D gravity is not an ensemble average of 2D some CFT theories. Very good. Okay, so now I will talk a little bit about this chaos in 3D gravity tormos. So what we have calculated is basically torus 4-point function. Why? Because this chaos, if you calculate you want to calculate this chaos, you want to calculate this OT, OC. So this is out of time order correlator, which is basically saying if you have 4 insertions, O1, O2, O3, O4, at times epsilon 1, epsilon 2, epsilon 3, epsilon 4, your epsilon 1, epsilon 2 is larger, epsilon 3 is larger, epsilon 4 is more larger. But when you calculate OTOC, this is the time order correlator. When you calculate OTOC, you shuffle one of them. So this becomes this. So this will become this. So these 4-point functions where you do time, where you relax the time ordering, you will get an imprint of chaos, and that we have calculated in our paper, which is basically we have calculated the torus 4-point block and using the cat matrix, where we have 4 super Liouville insertions on the torus, and you generally first calculate whatever your case is with the general epsilon 1, epsilon 2, epsilon 3, epsilon 4, and then you take into consideration what is your ordering. I mean, you can change the ordering to epsilon 1 going to. So this is basically changing channels from necklace channel to you have can go to the OPE channels. So these changing channels is done by basically this sort of transformation. So you can see here that if you have a S channel diagram, which is basically this, you can change it to the T channel by the fusion kernel. If you have a torus, which is basically this type of thing, you can change it to the other channel by using modular transformations. So there are different topological transformations. These are braidings, the initial one. So there are different topological transformations which you can do to change the channel and calculate whatever these 4-point functions these things are. So we have done it for the 4-point super Liouville conformal blocks, and before ending, we'll just talk about OTOC. So whatever you got is basically this structure. Now you can see the absolute value of OTOC is going down and down, and the real part of OTOC is going from below to up. And this is a non-normalized OTOC. I mean, you don't divide by this quantity. We have not done that, but this is the non-normalized one, where we have taken where we relaxed the time order correlator to by the out of time order correlator. And the way to do this is basically you start with the 4-point insertions OA, OB, OA, OB, which is basically a time ordered one, and you braid the 2 channels by suppling OA and OB. What you get OA, OA, OB, OB. So this thing is out of time ordered. I should say this thing is out of time ordered, because there is a OA, OB, OA, OB thing, and there is a OA, OA, OB, OB thing, which is time ordered. So from anti-time ordered thing, you can get the anti-time ordered thing by using the braiding transformation. By braiding, I mean if you have things like this, these 3 lines, you can braid it by using this. Okay, so this is called braiding. So you're changing the insertion order. Okay, so now I'll just keep this thing because this is more involved. So before ending, I would like to give some small summary and what are the future directions. So firstly, we have calculated the claim of Virasoro TQFT is that you can calculate the gravitational partition function, which is equal to the modular square of the Virasoro partition function. Then you sum over all possible modular transformations. And we have generalized to n equal to 1 super Liouville theory by super Virasoro TQFT. Now the easy generalization will be to calculate what is the. So we have calculated it for even spin structures. Now one can generalize it to odd spin structures. What happens for odd spin structures, and the modular sum, as we have seen that the modular sum changes from the Liouville one if you consider the odd spin structure. And eventually calculate the OTOC for the super torus with super Liouville method insertions. For this purpose, we first complete the necklace channel time order correlator. We also calculated for the so we have calculated for n equal to 1. So the generalization could be possible for n equal to 2. But the point is the Teichmuller TQFT blocks. I mean these braiding transformations, these fusion transformations are only known for n equal to 1. It is not known till now for n equal to 2. So it would be a good generalization to see what happens for n equal to 4 eventually, because there is a string dual of type 2B string theory in ADS5 cross S5 with n equal to 4 super yapping. So it will be and they will be important to keep what happens to the gravitational interpretation of these OTUCs. So and another thing we can do is the generalize to BMS things, BMS super torus, and we are calling it super torus because we have, instead of the upper half plane is basically containing Z, but we need to introduce Grassmannian numbers for n equal to 1 super Liouville, because there is a theta coordinate also. That's why it's called the super torus. Okay, so that's all. So thank you for your attention.
Thanks, Sounak. This is a very nice presentation, and we get a lot of things from your talk. And this is a time for questions. Are there any questions from the audience? Please unmute yourself. You can ask the questions if you have. Okay, so if there are no more questions, are there any questions? Okay. So if there are no more questions, then it clearly indicate that the talk is clearly understood. So, okay. So, Shaunak, you can just send your PDF file to me, and
Yes. Yeah.
this will be useful later. And
Yeah.
okay, we can stop here. Thanks again.
Yeah. Thank you. So we can discuss your question online if you wish. So
Yes, regarding this question, I will talk to you later.
yeah.
I would like to understand what is the meaning of this sum over topology as well as sum over geometry. This seems to indicate means in a condensed matter situation when I hope you remember the solid state physics in crystallography, we always taking the sum over all possible unit cell as well as sum over all possible reciprocal lattice vectors.
Yes.
Something is like that. The unit cell is something like that. The geometry.
So the point is, yes. So what you are telling is there is a connection. So the point is this comes from. So it's very deep, I guess. So the point is what I want to say. I don't know much about this, but so the if you have a manifold, let's say there is a 3D closed manifold, you start defining triangulating the surface. So you start defining simplices. You need to define symmetrical homology on that. So what is that? You start with, so what is symmetrical homology is basically you start with simplexes. You can have a small dot. You can have a line. You can have a tetrahedron. You can have a triangle. So why these, from where these things are coming? Why these specific things? Is basically the simplices are basically things where you have T0. So you start with, let's say, triangles. So in 3 dimension, you start with T0 plus T1 plus T2 less than 1. So this defines a triangle in 3D. Also, if you start defining in 2D, if you start defining T0 plus T1 less than 1, this will be less than equal to 1, which is basically a straight, crossing line in this two plane. So the point is, the initial thing you do is basically you triangulate the surface. You break the surface in all sorts of these triangles and so on. And whenever you do that, you will get a lattice. So
Yes.
this tensor network of all sorts of these triangles. And the thing you do is basically you can have also holes in this type of, when you fill up these things with. So you can have different simplices. You can have a triangle. You can have a tetrahedral. You can have a higher dimensional things. But whenever you start filling up these 3 manifold with these sorts of simplices, there is a joining rule. I mean, how would you join two triangles if it is sitting each of each other? So there is a large, so these are called Mera networks, something called Mera networks, and they use these things so much in this tensor network thing, where they have shown that you can calculate the gravity partition function using these Mera networks. So that is more prominent when you use this type of cell things. But I mean, there is also a way of using this TQFT that you are sort of doing things. But I mean, yeah, so there is a large sort of literature using this.
I got your point. I think we can discuss regarding these points more detail, more
Yes.
personally. So
Yes.
I think we can stop here. Thanks
Okay.
for your nice presentations. Bye bye.
Thanks. Bye.